In this video, I'm going to show how to build a high voltage multiplier that can generate 120,000 volts DC and make arcs up to 5 inches long. The circuit starts with a 12-volt ZVS driver, which is the exact same design as the one I used in my previous video on induction heating. The ZVS driver powers a flyback transformer I built myself, which puts out 10,000 volts of alternating current. That 10,000 volts is then stepped up and rectified by this ladder of diodes and capacitors to create 120,000 volts of DC. The trickiest part about this build is going to be the flyback transformer, which I'll need to wind myself to get AC. If you experiment with high voltage, you've probably seen a flyback transformer before. The ones you usually find on the internet look something like this, and they were meant to accelerate the electron beam inside CRT televisions. But since almost nobody produces CRTs anymore, there's a big leftover surplus of these things floating around. The problem is that all of these devices have an internal voltage doubler, which also rectifies the AC output by taking a voltage waveform centered at 0 volts and shifting it up above the 0 line. That could theoretically still be used for a voltage multiplier, but there's a few problems. 1, I need to match the capacitor values, but I don't know this capacitance. 2, I don't know the rating of this capacitor and how hard I can push it before it fails. And 3, I have no way to access the capacitor to repair or replace it because everything is potted in epoxy. The potting also causes problems cooling the transformer, and the transformer core is tiny, so it doesn't take much to saturate it, meaning there's a limit on the power that it can transfer. Because of all these problems, the best approach is for me to just wind my own flyback transformer from scratch. The secondary on this flyback burned out a while ago, so I recycled the core from it. Then I 3D printed a bobbin that I wound several thousand turns of 32 gauge wire around. To make sure the secondary didn't arc over to the primary, I wrapped several layers of polyethylene film around it and glued the film in place. Then I reassembled the core and connected the transformer to one of my pre-made ZVS drivers. At first it seemed to work well, but on the second test I noticed a major problem. The secondary windings were arcing to each other. This takes a ton of power away from the output and eventually destroys the transformer. So I had to go back to the drawing board and design a new secondary. The second version was wound with around 4,000 turns of 36 gauge, which turned out to be kind of a nightmare because it's incredibly fragile and almost invisible, which makes it really easy to break by accident. This time, I had the idea to put the transformer in oil to help insulate the windings and the core. I even degassed the oil with a vacuum pump to drive out any air pockets that might have been hiding between the windings. I let it sit for about 24 hours under vacuum, then tested it out. I didn't see any arcing in the windings, and the arcs I was pulling seemed to be decent sized, but it still seemed like a lot less power than I should be getting. At one point, I touched the primary winding while the transformer was energized, and it gave me a bit of a shock. So even though I didn't see sparks, it was definitely still happening. The inner windings were most likely arcing over to the core. The third time around, I decided I might have better luck if I just used some bigger, wider ferrite cores, so I got a few off Amazon to try them out. I also realized my turns ratio was way too high. The ZVS driver was driving my primary at around 38 volts with a 12 volt input, so if I wanted, say, 12,000 volts, I didn't need a 1,000 to 1 turns ratio, I only needed about 300 to 315. In this case, I designed the transformer output to be about 9,000 volts at 12 volts of input into the ZVS driver. So I built it with 1,100 turns on the secondary and 4 turns on the primary. Then I built the ZVS driver to power it. This time, it worked perfectly. Here you can see the power consumption. When the arc was drawn all the way out, the driver pulled nearly 30 amps. Here's what the transformer primary looks like on the scope. Without a load, it idles at about 31 kHz, but when an arc is pulled, the frequency goes to over 80 kHz. This is because the inductance of a transformer's primary goes down when a load is put on it, which increases the resonant frequency. Now that I've finally got a good AC flyback transformer working, let's start to assemble the multiplier itself. The diodes and capacitors will be mounted on this vertical rack and soldered together. Okay, let's give it a quick test. Works good, so now I'm going to start building the enclosure. The multiplier will be housed inside a PVC tube filled with oil. The oil will help keep the components from arcing, and it will also keep them cool. This screw will be the high voltage electrode, which will be wired to the multiplier's output inside the tube. The multiplier rack will be glued to this base, which the PVC tube will slide over. It also has these two small holes that are sized for banana jacks. The inputs to the multiplier are soldered to the input jacks. The tube slides over it, and then everything is filled with oil. Now everything is connected up and ready for a first test. I wanted to see if I could get arcs to jump through this light bulb the way they do with the Tesla coil, and it sort of worked, but not as dramatic. The last thing I want to demonstrate is the powerful static charge the multiplier can produce. When these thin strips of paper are raised up to 120,000 volts, they repel each other and stand up. The whooshing sound you hear is actually the ion wind caused by the corona discharge. It's strong enough that I can feel it about 2 feet away, and it causes the paper to sway around. Well, that's all for now. Thanks for watching.